still confess to this day I've not read all of the book, but at least at this point, I went through and found the parts that were most interesting to me, which were the total parts, and skipped them out of the book parts. And I did read those. I did try.
Zero friends, 14
The beginning of
ops.
Infinity is similar. Everybody has it on their bookshelf in my social
75, okay? 3/4 of the way,
You go back
you
to this
know?
point that was
Gonna
first.
make who you are, gonna make a person.
How
to make a personality.
I don't want to read all the books.
Here
I
we
just
are,
want to read
though.
the best 100.
Doing work,
I
getting it
was
done.
stuck.
You guys heard that new Kendrick
I'm only
album?
going to read the beginning of the fabric.
Just me?
Over and over again.
Not a problem.
If I had read the
Rolling through.
I would know a lot more because then I would have chosen the right books and the right authors for the subsequent.
Full
It's
bottle
gonna
one
be a hard
fan,
book to follow. You should buy a hardcover.
90 out, 16 in.
And the audio. Get it
Socks.
every way possible.
All the way up.
We're sitting and understand all the
Big
points.
sphere possible.
But we're
Rolling in.
The difference with the beginning of Infinity, you're getting a world. You're not being given the standard take from physicists about how to understand quantum theory. You're not being
Good to
given
go.
the standard take of how to understand knowledge
Locked
from
in.
philosophers. And you're certainly not being given the standard take of how to understand
Feeling tight.
mathematics from mathematicians. Deutsch is qualified in all these areas. He's expert in all these areas.
So the worldview itself, what's at the
Okay,
core?
right.
Deutsch's worldview is that reality is comprehensible, problems are soluble. It's a deeply rationally optimistic worldview. It believes in good explanations, good scientific explanations, and progress. Progress is inevitable as long as we have these good explanations. Good explanations have tremendous reach. They are acts of creativity.
Sea level.
Humans are problem solvers and can solve all problems. All sins and evil are due to a lack of knowledge. One can be optimistic about constant progress. That's what the title, The Beginning of Infinity, refers to, that we're at the beginning of an infinite series of progress. It's a very optimistic take. It believes that we are at home in the universe is ours as a resource to learn about and exploit, that material wealth is a set of physical transformations that we can affect, that everything that is not forbidden by the laws of physics is eventually possible through knowledge and knowledge creation. He also talks about how humans are universal explainers, that anything that can be known and understood can be known and understood by human beings, the computation power of the human system. It's all knowable by humans. We're the beginning of an infinity of knowledge, and as we understand things using good explanations and create new theories that are constantly being destroyed and replaced by better ones, there's no end point in sight, there's no perfection. Every theory can be falsified and improved, that we are on our way to being able to do everything that is not forbidden by the laws of physics.
What does the transform is knowledge. We can take some raw material that had no particular use, and within that raw material we might find uranium nuclei, which then can be used in a nuclear reactor to create energy or bombs. We can find within something that for almost the entire geological existence of the Earth sat there inert and would have done nothing absent people. People are the entities within the universe that create explanations. They're able to explain what raw materials might be transformed into. Now, what are they transforming these raw materials into? Civilization. People creating knowledge end up becoming literally a force of nature. If we seek to explain something like the shape of a galaxy or the shape of a star, any astrophysicist will give you a story based upon the known laws of physics, about how gravity will pull things into spheres, how the laws of thermodynamics will cause certain kinds of gas to heat up and expand. All of the known laws of physics are sufficient to explain what we see out there in the cosmos. But the laws of physics alone will not be able to explain the appearance of Manhattan. We have to invoke things other than merely fundamental laws of physics. We need to invoke the existence of people and their capacity to explain the world scientifically, philosophically, politically. Because it's all of those things that will come together to explain why we have certain structures like skyscrapers in Manhattan. This is a profound idea. It's an idea that seems to have been overlooked by scientists. Many of them have a reductionist idea about how to explain what we see in our environment. They seek to explain only the natural phenomena of our environment. Of course, everyone wants to know how the laws of nature work. But if we want to understand how the universe, from this point onwards, whether it's locally on our own planet, eventually the solar system, eventually the galaxy, is going to evolve over time. We're going to have to talk about the knowledge that people create and the choices that we're going to make into the future. This is a different vision of the place of people in the universe. Stephen Hawking famously said, people are nothing special. People are chemical scum on a very typical planet orbiting an average star in the outer suburbs of a very typical galaxy, which is one among hundreds of billions of galaxies in the universe. This vision of what people are and of what the planet Earth is, it's true in a trivial sense, but it misses the point. People are a hub of a planet. We are, so far as we know, the sole place in the universe which is creating knowledge, an open-ended stream of knowledge that could transform the rest of reality. In the same way that gravity is able to pull that galaxy into a particular shape, knowledge in the future will be able to shape the course of the planet, the solar system, eventually the galaxy. We will have this profound impact on everything that we can see around us. And there's nothing that the laws of physics, the laws of chemistry, or even the laws of biology can predict what is going to happen in the future. The attempt to predict the future growth of knowledge is impossible. That's the nature of knowledge, because knowledge creation is genuinely an act of creation. It is bringing something into existence that wasn't there prior.
If you could predict it, you would have invented it already. A lot of the deeply pessimistic worldviews come from a straight line linear extrapolation of negative trends while ignoring positive trends. Positive trends mostly come from creativity and knowledge creation, and it's inherently unpredictable. So every generation has its doomsayers and Cassandras, the modern Malthusians, who say, on this trajectory, we're all going to die. They're very popular for the same reason that zombie movies and vampire movies are popular. But the reality is that they cannot predict what we're going to do in the future that is going to improve our quality of life and save us from inevitable ruin. The value is in the knowledge, and the knowledge is inside the observer and the creator, in other words, the human. It's not inside the thing itself. For example, oil is useless unless you know how to refine it, burn it, and use it for combustion. Information is useless unless there's a brain there to receive it. There could be a signal broadcasting English into outer space, but if there isn't a creature capable of understanding what that language is and how it works and who's conveying it, then it's just modulated electromagnetic frequencies that don't mean anything. So a lot of the information, a lot of the value is within a particular knowledge-bearing entity. As science grows its reach, we've gotten to a very reductive science where we break things down to smaller and smaller pieces, and then we try and explain things on the basis of that. And there is a counter-trend in science, which is complexity theory. We talk about emergent properties and higher level systems, where we're starting to now look at systems as they operate chaotically and unpredictably at a micro level, but at a macro level, we can make certain statements about them that do have explanatory power. So humans are unique in our capability to understand things. There's a phrase that you're going to hear both Brett and I use over and over again, and that phrase is good explanations. Good explanations is Deutsch's improvement upon the scientific method. At the same time, it's beyond science. It's not just true in science, but in all of life, we navigate our way through life, and we do it successfully by creating good explanations. If you take away nothing else, try and understand what a good explanation is. A good explanation, first and foremost, is testifiable/falsifiable. You can run some experiment in the real world to see if it's true or not. Stepping back from that, it's a creative explanation. It looks at something that's going on in the real world and says, this is why it's happening. It is a creative leap that says this is the underlying explanation for how the thing works. For example, when I talk to my young kids and we're out watching the sunset, I keep telling them, is the sun setting? Is the sun going somewhere? Is the sun moving? Or is it maybe we're moving? And we're moving in such a way that it looks like the sun is setting, which is the proper explanation. Because looking at it naively, you would think the sun is hurtling across the sky and there goes the sun again going around the earth. But that may not be the only explanation. There is a completely creative explanation that seems to fly in the face of the obvious observation of the sun's movement, but could also fit the facts, but it requires some creativity, and that creative explanation is that the earth is rotating. Good explanations don't have to be obvious. They're not derived from just looking at what happened in the past, but they are testable. There are experiments we can run to figure out, is it the sun that is going around the earth, or is it the earth turning? Brett, would you say that a scientific theory is a subset of a good explanation?
Yes, they're the testable kinds of good explanations. Falsifiable theories are actually a dime a dozen. This doesn't tell you anything about the quality of the explanation you're being given. The example that's used in fabric reality is the grass cure for the common cold. If someone comes along to you and says, if you eat 1.0 kilograms of grass, it will cure your common cold, they have a testable theory. The problem is that no one should test it. Why? Because they haven't given you an explanation as to what the mechanism is that will enable grass to cure the common cold. And if you do eat the 1.0 kilograms of grass and it doesn't cure your cold, they can turn around and say 1.1 kilograms.
Right, or you need a different kind of grass, or you need to always do it on a different day.
It's always testable, but you're not getting anywhere, you're not making any progress.
So I think the second piece of good explanation is hard to vary. It has to be very precise, and there has to be a good reason for the precision. The famous example used in Zwfity is the why do they have seasons on the earth? And there was the old Greek explanation, well, it's driven by Persephone, the goddess of spring, that's when she believed Hades, and there's this whole theory involving gods and goddesses. Not only was that not easily testable, it was very easy to vary. Persephone could have been Nike, and Hades could have been Jupiter or Zeus. It's very easy to vary that explanation without the predictions changing. Whereas if you look at the axis tilt theory, it's saying the Earth is angled at 23 degrees relative to the Sun, therefore we'd expect the Sun to rise here in the winter and over there in the summer. The facts of that are very hard to vary. It makes risky and narrow predictions. You can predict the exact length of summer and winter at different latitudes, and you can test them very precisely. So beyond it being a creative theory that is testable and falsifiable, it should be hard to vary the pieces of that theory without essentially destroying that theory. You certainly don't want to vary it after the fact, like your grass example. Oh, it was 1 kilogram, now it's 1.1, now it's 1.2. Finally, the predictions that it makes should be very narrow and precise, and they should be risky. For example, I believe in relativity, was it Eddington who did the experiment and showed that star light gets bent around an eclipse? And that was a prediction that Einstein had made in relativity, which turned out to be true. That was a risky prediction that took a long time to confirm.
That's an excellent example of what's called a crucial test, which is sort of the pinnacle of what science is all about. If we do a test and it doesn't agree with a particular theory that we have, that's problematic. But that doesn't mean that it refutes the theory, because if you were to refute the only theory that you have, where do you jump to? You don't have any alternative. If we were to do a scientific test tomorrow and it was inconsistent with the theory of general relativity, then what? There is no alternative to general relativity. In fact, when you have many experiments over the years that seem to have been inconsistent with general relativity, guess what? They will turn out to be faulty. If you have to choose between whether or not general relativity has been refuted by your test, or your test is flawed, go with the fact that the test has been flawed. In the case of Eddington's experiment, we have two viable theories for what gravity is. We have Newton's theory of universal gravitation on one hand, and we have Einstein's general theory of relativity. This experiment was described of how much the light was bent during the solar eclipse. The correct way of describing what happened is not what we showed that general relativity was correct in some final sense, but rather we refuted Newton's theory of gravitation. Newton's theory was ruled out because it was inconsistent with the test, while general relativity was consistent with the test. This doesn't mean that general relativity is the final word in science. It means it's the best theory we have to have. There's a whole bunch of reasons that we might think general relativity ultimately has to turn out false. We never have the final word, and that's a good thing. That's a really positive, optimistic thing, because it means we can keep on improving, we can keep on making progress, and we keep on discovering new things. There is no end of science. The long thought about idea that so many have feared that one day progress will come to a halt, that science will end. In fact, we are at the beginning of infinity, and we will always be at the beginning of infinity, precisely because we can improve our ideas. We're fallible human beings, so none of our theories are perfect, because we aren't. Our process by which we create knowledge is either it's error-prone.
There are two other scientific thinkers that I like who are unrelated to David Deutsch, but come to very similar conclusions. One is Nassim Taleb, who has popularized the idea of the black swan, which is that no number of white swans disproves the existence of a black swan. You can never conclusively say all swans are white. You can never establish final truth. All you can do is work with the best explanation you have today, which is still better than ignorance, far better, But at any time, a black swan can show up and disprove your theory, and then you have to go find a better one. The other fellow who I find fascinating is Gregory Chapin. He is a mathematician who is very much in the Kurt Gödel vein, where he tries to explore the limits and boundaries of what is possible in mathematics. One of the points that he makes is that Gödel's incompleteness theorem doesn't say that mathematics is junk. It's not a cause for despair. Gödel's incompleteness theorem says that no formal system, including mathematics, it can be both complete and correct. Either there are statements that are true that cannot be proven true in the system, or there will be a contradiction somewhere inside the system. So this could be a cause of despair for mathematicians who view mathematics as this abstract, perfect, fully self-contained thing. But Chapin makes the argument that actually it opens up for creativity in mathematics. It means that even in mathematics, you are always one step away from falsifying something and finding a better explanation for it. It puts humans and their creativity and their ability to find good explanations back at the core of it. And at some deep level, mathematics is still an art. There's very useful things that come out of mathematics that are still building an edifice of knowledge. But there is no such thing as conclusive, settled truth. There is no settled science. There is no settled mathematics. There are good explanations that will be replaced over time with more good explanations that explain more of the world.
This is something that we inherit from our schooling more than anything else. It's part of our academic culture and breeds into the wider culture as well. People have this idea that mathematics is this pristine area of knowledge where what is proved to be true is certainly true. Then you have science, which doesn't give you certain truth, but you can be highly confident in what you discover. You can use experiments to confirm that what you're saying appears to be correct, but you might be wrong. And then, of course, there's philosophy, which is a mere matter of opinion. This is the hierarchy that some people inherit from school. Mathematics is certain, science is almost certain, and the rest of it is more or less a matter of opinion. This is what Deutsch calls the mathematician's misconception, is that mathematicians have this intuitive way of realizing that their proof, their theorem that they've reached by this method of proof, is absolutely certainly true. In fact, it's a confusion between the subject matter and our knowledge of the subject matter. Very quickly compare it to physics. We have this domain called particle physics, and the deepest theory we have in particle physics is called the Standard Model, which describes all of the different fundamental particles there are and the interactions between those fundamental particles, the forces that exist between them, and the gauge bosons which mediate the force between particles like electrons and protons and neutrons. Now, what is matter made of? We would say matter is made of these particles, the particles described by the Standard Model of physics. But does that rule out the fact that these fundamental particles might themselves consist of even smaller particles? We have this idea of string theory. So our knowledge of what the most fundamental particles are and what in reality the most fundamental particles are is different. So too in mathematics. Deutsch explains that mathematics is a field where what we're trying to uncover is necessary truth. The subject matter of mathematics is necessary truth. In the same way that the subject matter of particle physics are the fundamental particles. But because the subject matter of fundamental particle physics are the fundamental particles, that doesn't mean you actually find the fundamental particles. All it means is that you have found the smallest particles that your biggest particle accelerators are able to resolve. But if you had an even bigger particle accelerator, you might find particles within those particles. This has been the history of particle physics, by the way. We used to think that atoms were fundamental. Then, of course, we found that they contain nuclei and electrons. In the nuclei, we found out there were protons and neutrons. Inside the protons and neutrons, we found out they were made up of quarks. And that's where we're at right now. We're at the point where we say that the quarks are fundamental and the electrons are fundamental. But that doesn't mean that we're going to end particle physics right now. What we need are further theories about what might be inside of those really small particles. Comparing that to mathematics, if necessary truth is the subject matter of mathematics, our knowledge of that necessary truth is what mathematicians are engaged in. They're engaged in creating knowledge about necessary truth. And because a mathematician has a brain, which is a physical object, and all physical objects are subject to making errors of degradation via the second law of thermodynamics, or simply just the usual mental mistakes and errors that any human being makes, a mathematician is just as fallible as anyone else, then what they end up proving could be an error.
So if I understand this point, even mathematics is capable of error because mathematics is a creative act. We're never quite done. There could have been a mistake in your axiom somewhere. Ultimately, even mathematics is a creative act and can have error within it.
All knowledge is conjectural. It's always being guessed. It's our best understanding at any given time. You're right to say that the axioms might be incorrect. How do we know that an axiom is incorrect? Traditionally, the answer has been because it's clearly and obviously the case. How can you prove that x plus 0 must equal x? Well, you just have to accept that it's true. But if we consider something like Euclid's elements, for example, draw 2 points on a piece of paper. Now, through those 2 points, a unique straight line can be drawn. This was accepted as true for centuries. Anyone listening might want to try to experiment themselves. Take a piece of paper, take a pen, draw 2 dots on the piece of paper. Now, how many unique straight lines can you draw through those 2 dots? It should be fairly obvious to you that only one such line can be drawn. However, we now know that's false. I just want you to reflect as you're staring at a piece of paper through which only one straight line is being drawn. You have the feeling of certainty. You are absolutely sure that you're not wrong. This feeling is something you should always be skeptical of. Because when people have been absolutely certain, even in a domain as apparently full of certainty as mathematics, they've been shown to be wrong. So how can we show it? Here's what we do. And you might think that I'm cheating, but then again, you have to reflect on it. Did you understand what I was saying when I first told you to draw a unique straight line through these 2 points? Here's what I want you to do. Bend the piece of paper. Think in 3 dimensions. Wrap the piece of paper around a basketball. Now consider the ways in which you could draw a straight line through those 2 points. You can punch a hole through one of those dots with your pen and push it out through the other side, through the other hole. And now you have a different straight line. You have the straight line that is drawn with your pen, and you have a straight line that is literally your pen that is being pushed through these 2 dots. So your initial feeling of absolute certainty that only a unique line can be drawn through these 2 dots is false. And you might be thinking, that's unfair, that's cheating, you were thinking in 2 dimensions. No, you were thinking in 2 dimensions. I wasn't. I was thinking in more dimensions than that. Karl Popper has this wonderful saying, it is impossible to speak in such a way that you cannot be misunderstood. This is always the case. So even in mathematics, where we try and be as precise as possible, it's possible for people to make errors, to think false premises about what the argument is that they're trying to make. And by the way, this particular example of Euclidean geometry, because geometry was traditionally always done in 2 dimensions on a piece of paper, was resolved by various people and led to geometry in curved space, which led to Einstein coming up with the general theory of relativity. So it is questioning these deepest assumptions that we have, where we think there's no possible way we can be mistaken, that leads to true progress, to genuine fundamental change in the sciences of the world.
You said that we went from atoms in the time of Democritus down to nuclei, and from there to protons and neutrons, and then to quarks. It's particles all the way down. So paraphrase 5 minutes, we can keep going forever. But it's not quite forever, right? At some point you run into the Planck length.
There's the Planck time, there's the Planck length, there's even the Planck mass, which is actually quite a large mass. These things don't have any physical significance. It's not like the Planck time is the shortest possible time. And it's not like the Planck length is the shortest possible. The reason for that is because these Planck things are part of quantum theory. But length is not described by quantum theory. It's described by the general theory of relativity. And in that, space is infinitely divisible. There is no smallest possible length or time. This illuminates an ancient tension between the discrete and the continuous, because quantum theory seems to suggest that things are discrete. For example, there's a smallest possible particle of gold, the gold atom. There's a smallest possible particle of electricity, the electron. There's a smallest possible particle of light, the photon. In quantum theory, we have this idea of discreteness. There is a smallest possible thing from which everything else is built. But in general relativity, the idea is the opposite. It says things can continuously vary. And if the mathematics requires that things be continuously variable so they can be differentiated and so on, the idea there is that you can keep on dividing up space and keep on dividing up time. So physicists understand that there is this contradiction at the deepest level of our most foundational explorations of physics. And it's one of the reasons why there are these attempts to try and unify quantum theory and general relativity. Because what is the fundamental nature of reality? Is it that things can be infinitely divisible? Or is it that we must stop somewhere or other? Because if it's infinitely divisible, then quantum theory might have to be subservient to general relativity, but we just don't know.
There goes my solution for Zeno's paradox, which is before you can get all the way somewhere, you have to get halfway there, and before you can get halfway there, you have to get a quarter of the way there, and therefore you'll never get there. One way to get past that is to say even a series of infinite things can have a finite sum. Just run the infinite series and sum it, and we learn pretty early on that converges. But another thought I had was that you have to cover a minimum distance, a Planck length, and therefore you will get there. It's a finite series of steps, but you're saying we just don't know.
Yes, so if the laws of physics say that we can cover 1 metre in a certain time period, then that's exactly what we do. And our current understanding of the laws of physics say precisely that. So Zeno's paradox is resolved simply by saying that we can cover this space in this amount of time. It's silent on whether or not space is infinitely divisible. When someone asks, is space infinitely divisible? Then I would say, yes it is. And they might turn around and say, how do you know? I would say, general relativity. How do I know that's true? Well, I don't know that it's true. However, it is the best explanation that we presently have of space-time. And then they might get into a discussion about, well, if it's infinitely divisible, then you're presented with Zeno's paradox all over again. And I would say, no, you refute that by a simple experiment. So we don't know how it is that we can travel through all of these infinite points, if in fact there are infinite points. Zeno's paradox is about the domain of pure mathematics, but we don't live in a world of pure mathematics. We live in a world of physics. And if the physics says that we can transverse an infinite number of points in a finite amount of time, then that's what we'll do, regardless of what we don't understand.
Every mathematical theory is held inside a physical substrate of a brain or a computer. You're always bound by the laws of physics, and these pure abstract domains may have no mapping to reality.
The overwhelming majority of theorems in mathematics are theorems that we cannot possibly prove. This is Gödel's theorem. And it also comes out of Turing's proof of what is and is not computable. These things that are not computable vastly outnumber the things that are computable. And what is computable depends entirely upon what computers we can make in this physical universe. The computers that we can make must obey our laws of physics. If the laws of physics were different, then we'd be able to prove different sorts of mathematics. And this is another part of the mathematician's misconception. They think they can get outside of the laws of physics. However, their brain is just a physical computer. Their brain must obey the laws of physics. If they existed in a universe with different laws of physics, then they could prove different theorems. But we exist in the universe that we're in, so we're bound by a whole bunch of things, not least of which is the finite speed of light. So there could be certain things out there in abstract space which we would be able to come to a more full understanding of if we could get outside of the restrictions of the laws of physics here. Happily, none of those theorems that we cannot prove at the moment are inherently interesting. Some things can be inherently boring, namely all of these theorems which we cannot possibly prove is true or false. Those theorems can't have any bearing in our physical universe. They have nothing to do with our physical universe. And this is why we say they're inherently uninteresting. And there's a lot of inherently uninteresting things.
Does probability actually exist in the physical universe, or is it a function of our ignorance? If I'm rolling a dice, I don't know which way it's going to land, so therefore I put in a probability. But does that mean that there's an actual probabilistic, unknowable thing in the universe? Is the universe flipping a coin somewhere, or is it always deterministic?
All probability is actually subjective. Uncertainty and randomness are subjective. If you don't know what the outcome's going to be, so you roll a dice, that's because you individually do not know. It's not because there is uncertainty there deeply in the universe. What we know about quantum theory is that all physically possible things occur. This leads to the concept of the multiverse. And rather than refute all of the failed ways of trying to understand quantum theory, we're just going to take seriously what the equations of quantum theory say. What we are compelled to think about quantum theory given the experiment is that every single possible thing that can happen does happen. This means that there is no inherent uncertainty in the universe because everything that can happen actually will happen. It's not like some things will happen and won't happen. Everything happens. Now you occupy a single universe. And in that universe, when you roll the dice, it comes up 2. But we know somewhere else in physical reality it comes up 1, somewhere else 3, 4, 5, and a 6.
If I'm rolling 2 dice, then the universe in which they sum up to 2 is less than the number of universes in which we roll a 7, because that could be 3 or 4 or 5 or 2 and so on. So the number of universes still does correspond to what we calculate as the probability.
Yes. This leads to what Deutsch calls the decision theoretic way of understanding probability. Decision theoretic means
Come on, get into it.
assumes proportionality between universes, this way of splitting things up. So if we're rolling 2 different dice, then the universes proportion themselves into measures. And what a measure is a way of talking about infinities.
There is a video on YouTube which has Deutsch explained the famous quantum double slit experiment, which was about particle wave duality. Is light a particle or a wave? You pass it through a slit depending on whether there's observer and interference or not, or ends up in a wave pattern, ends up as individual photons. And this is the famous experiment which has baffled people for a long time and caused them to revise their worldview. The one that led Einstein would say God does not play dice with the universe.
Correct. Einstein was a realist. At the time, the founders of quantum theory were trying to develop a good explanation of what precisely was going on with these experiments in quantum theory. Einstein rejected all of them on the basis that they weren't realistic, and he was right to do so, because none of them made any sense. And to this day, none of the other alternatives make any sense. Now, Einstein didn't know about the multiverse. We had to wait until Hugh Everett in the 1950s was able to devise a simple, realistic way of understanding quantum theory. But if I go back to this idea of the double slit experiment, it is often claimed that particles have a duality to them. Sometimes they're particles and sometimes they're waves. The electron, for example, given certain experiments, will behave like a wave. And in other experiments, it behaves like a wave. People who hear this think, well, okay, that kind of explains what's going on. For example, in the photoelectric effect, you shine a light at electrons, which literally means you're firing a photon, a particle of light, at an electron. And you can knock the electron out of it. This is supposed to be proof positive that light, in the form of photons, and electricity, in the form of electrons, are both particles, because they're bouncing off one another. This is what particles do. Waves don't do that. You watch water waves at the beach, you see they pass through each other. They don't bounce off one another. Waves will bounce off particles, but they won't bounce off each other. Prior to Young's twin slit experiment, he actually relied upon Newton's ideas of light. And Newton's idea was that light was corpuscular, as he said. It was made of particles. And then Young came along, and he shone a light through 2 slits cut into a piece of paper, and what you find when you project that light onto another sheet of paper is not just 2 beams of light. You find what's called an interference pattern, where the light has interfered with itself. In the same way that when waves pass through small apertures, natural geological gaps, they will interfere with one another. They produce crests in some places and troughs in others. They can cancel each other out. This was supposed to be proof for some of the early physicists that light, in fact, was a wave. And now we get to quantum theory, and we find that things that we thought were certainly particles like electrons, when we do the same experiment with them, they interfere with one another. So it appears as though we've got particles acting like waves and waves acting like photons. The resolution to this is not to admit nonsense. So this is what often is explained in quantum theory lectures at undergraduate level, is that you have to accept that something like a photon is born as a particle, it lives as a wave, and then it dies again as a particle, which is nonsense. And the reason that's nonsense is because the photon doesn't know that it's alive and it's dead. It doesn't know what experiment it's participating in. So we have to come to a deeper understanding of how to explain what is going on in this double slit experiment. Because if we fire either a photon or an electron at that double slit apparatus, and we put a detector at either of those slits, then we will detect a particle. So we can detect that we fired a particle. We can detect that a particle is going through those slits, and we can detect a particle at the projection screen as well. When you do this experiment in the laboratory using electrons, you can see the dots where the electrons strike hitting the screen, but you don't get a simple pattern that you expect. If you're firing cannonballs at a wall where there are 2 holes in the wall through which the cannonballs can go, you would expect that all the cannonballs are going to go through those two holes and land in one of two positions behind the wall. But with particles at the quantum level, that's not what happens. Something is going on. And the only explanation is that when we fire a photon, there's the photon that we can see in our universe, but there's also photons in other universes passing through the apparatus that we cannot see. And these photons are able to interact with the photon that we are able to detect. This is where the concept of interference comes in. Interference is an old concept in physics. It goes back to waves. Waves certainly interfere. But we need to understand the way in which particles can interfere one with another. Particles that we can observe and particles that we can only assume to observe given these experiments. And this is why we are forced into acknowledging the existence of these other particles. And not only these other particles, but other universes in which these particles exist. Now, people might object to this point and go, how dare you invoke in science things that cannot be seen, things that cannot be observed? This is completely antagonistic towards the scientific method, surely. And I will say to anyone who's thinking about that now, almost everything of interest that you know about science is about the unobserved. Let's consider dinosaurs. Dinosaurs are unobserved. You say, oh, hold on, I've been to the museum, I've seen a dinosaur. No, you have seen a fossil. And a fossil isn't even a bone. It's an ossified bone that has been metamorphosed into rock. So no one has ever seen a dinosaur. We have seen things that look like dinosaurs and interpreted them to be huge reptilian bird-like creatures that when we assemble their skeletons, we make up a story about what this thing was that walked the earth tens or hundreds of millions of years ago. In the same way, no one has ever seen the core of the sun, and no one will ever observe the core of the sun. But we know about stellar fusion. We know that hydrogen nuclei are going to crash together there to form helium and in the process producing heat. We don't see the Big Bang, we don't see the movement of continents, almost everything of interest in science we do not observe.
Even many of the things that we say we have seen, we've actually just seen instruments detect those things. So we're watching the effects through instruments and then theorizing that there are other universes out there where the photons are interacting with the photons that we can see.
There are many scientists, philosophers who've talked about this concept of the multiverse. But this is a very strict, very sober understanding of what a multiverse is. All of these universes in this multiverse obey the same laws of physics. We're not talking about universes where there are other laws of physics. This should be no more surprising than historically when it used to be thought that the universe consisted of our planet, and around our planet orbited everything else. Other planets, stars, the sun, the moon orbited around us, existed on this tiny planet. Then our vision of reality got expanded. We realized, in fact, we were not at the center of the universe. The sun was at the center, and these other planets were, in fact, bigger in some cases, in the case of Jupiter, Saturn, and asteroids, bigger than what our planet Earth is. The sun was a lot bigger than what we are, so our universe became larger. Then we realized that we were just one star system among many in a huge galaxy of hundreds of billions of stars. And later we realized that this galaxy is one of hundreds of billions of galaxies. So the history of ideas and the history of science is a history of us broadening our vision of exactly how large physical reality is. And this is another step in that general trend. And we should expect it to continue. It shouldn't be that hard for people to accept that this is the way to understand this. Do you know everything about quantum theory and how this multiverse works? No, we haven't united this multiverse with general relativity. We need a space-time or a geometry of the multiverse, but we don't have that.
So getting back to good explanations, where do these explanations come from? There's currently an obsession with induction. Induction being the idea that you can predict the future from the past. You can say, I saw 1, then 2, then 3, then 4, then 5, so therefore next must be 6, 7, 8, 9. There's a belief that this is how new knowledge is created, this is how scientific theories are formed, and this is how we can make good explanations about the universe. What's wrong with induction, and where does new knowledge come from?
You did mention the black swan earlier, and I'd like to go back to that. The black swan is an example that various people have used over the years in order to illustrate this idea that repeatedly observing the same phenomena over and again should not make you confident that it will continue in the future. In Europe, we have white swans, so any biologist who's interested in birds, observing white swan after white swan. and apparently concluding on that basis that therefore the storms are one. Then someone travels to Western Australia, and there you notice that there
Rock,
are storms that otherwise
nation,
look identical to the ones in
power.
Europe, but they're black.
Come on.
Let's consider another example of induction. Ever since the beginning of your life, you have observed that the sun has risen. Does this mean that scientifically you should conclude the sun will rise tomorrow and rise every day after? This is not what science is about. Science is not about cataloguing a history of events that have occurred in the past and presuming they're going to occur again in the future. Science is an explanatory framework. It's an error-correcting mechanism. It's not ever a perform the sun always rose in the past, therefore it rise in the future. There's all sorts of ways in which we can imagine the sun won't rise tomorrow. All you need to do is to take a trip to Antarctica. And there, for some months of the year, the sun doesn't rise at all. If you go to the International Space Station, you won't see the sun rise once per day and set once per day. It will rise and set repeatedly over the course of your very fast journey around the Earth. There's another example from science like this. On a heat source, put a beaker of water, then put a thermometer into that water and turn on the heat source. Then record, as the time passes, what the temperature of the water is. You would notice that the temperature of the water will increase. You can do this with a saucepan at home. So long as the heat source is relatively constant, the temperature rise will be relatively constant as well. So after 1 minute, the temperature might go from 20 degrees Celsius to 30 degrees Celsius. Imagine every minute climbs by another 20 degrees.
But at some point it's installed, right? It's the boiling point.
Precisely. Now, if you're a thoroughgoing inductivist, or even a Bayesian reasoner, and you don't know anything about the boiling temperature and what phenomena happens at that temperature, you can join all of those lovely lines into a perfectly diagonal straight line and extrapolate off into infinity. After 2 hours,
Every day.
according to your Bayesian reasoning,
Every
according
day.
to your induction, we should assume that the temperature of that water will be 1,000 degrees Celsius. But of course, this is completely false. What actually happens is once it starts boiling, it stays at its boiling temperature. We get a plateau. And this plateau of temperature, about 100 degrees Celsius, remains there until all the water boils away. Now, there's no possible way of knowing this without first doing the experiment or having already guessed via some explanatory means what was going to happen. No method of recording all of these data points and extrapolating off into the future could ever have given you the correct answer. The correct answer can only come from creativity. And notice that science is not about predicting where the trend starts and where the trend goes. In fact, if we want to explain what's going on with the water, we refer to the particles and how as the temperature increases, the kinetic energy of the particles starts to increase, which means the velocity of the particles starts to increase. Eventually, those particles in the liquid state achieve escape velocity from the rest of the liquid. At this point, we have boiling. But that escape velocity, the technical term is latent heat, requires energy. And for this reason, we can have heating of something like water without any temperature increase. That's what science is. That whole complicated story about how the particles are moving faster, this invocation of the term latent heat, it's not about trends and predictions, it's about explanation. Only once we have the explanation can we in fact make the prediction.
Going even further, it's not just science. When we look at innovation and technology and building, for example, everything that Thomas Edison did and Nikola Tesla did, these were from trial and error, which is creative guesses and trying things out. If you look at how evolution works through variation and then natural selection, where it tries a lot of random mutations and it filters out the ones that didn't work. So this seems to be a general model through which all complex systems improve themselves over time. They make bold guesses and then they weed out the things